Okay, so this is a quick checkpoint for you to get familiar with how to canceling the component. Okay, so here it says the figure here shows three non-conducting rod. Non-conducting rod means the charge are not free to move. Okay, so the charge must be fixed at that position. Okay, one circular and two straight. Okay, so this is circular. The B and C are straight. Each has a uniform charge magnitude, Q, along its top half, and then another another along its bottom half. So for each rod, what is the direction of the net? Okay, it don't ask you what is the magnitude because it doesn't give you anything. It only asks you the direction of the E field at the point P. Okay, so the idea here is like, so this is a negative Q. Okay, so at point P, it will be somehow pointing to this direction. Yeah, not necessarily 45 degrees, but at least something like that. And then, because it is a negative charge, okay, so the E field must be pointing towards this circular arc. And then as much as this is positive, okay, so this one must be point to the top right. Okay, so in that case, okay, after adding up together, it will be like pointing to the positive y-axis. Okay, positive y-axis. Positive y-axis. And then for the second case, okay, so for the upper part, okay, actually the whole rod has a positive charge. Okay, so for the point P, okay, so when you consider this part, it will be pointing to somewhere like this, okay, to the bottom right. Not sure what is the angle, because you don't know how long is it and then how long is this distance. Okay, but anyway, the total E field generated by the top half will be somehow pointing to the bottom right. And then similarly, for this part, it will be pointing to the top right. Okay, so you will know that. Okay, so the total E field will be point to the positive x-axis, like this. Okay, so finally, this one, okay, pointing to the bottom right. This one pointing to the bottom left. Okay, so something like this. Something like this. Okay, so it's very trivial. This part is the same. Okay, so this one will be the same. This is positive, this is negative. Okay, so opposite side. So so after adding up, it will be negative y-axis. Okay, so very simple. So just get you familiar with what is the how to cancel the component, okay, or how to determine the direction of the E field, so that you know which component you should integrate, which component you don't need to do anything. Okay, so this part, is another one. So this is the E field generated by a charged disk. Okay, so the previous case is a ring. Okay, this one is a disk. Okay, so here. Okay, so here we try to use what we get previously. Okay, so we consider we know the DE generated by a ring. Okay, even though we draw it with a thickness, but still we can consider the thickness is infinitely short. Okay, so we consider this is a dr actually tends to 0, because so that is the infinite small length of dr here. Okay, so according to the previous case, okay, actually this 2216, okay, actually this formula, okay, we will know, okay, if we have a ring, okay, the E will be like K times QZ over C squared plus capital R squared to the 3/2 power. Okay, here we only consider, the ring only have a dq, So we just change this DQ, this Q to DQ and then DE to DE. Okay, so that is this case. Okay, so previously we get this one. Okay, but here we try to change this Q into DQ and then E into DE. So nothing special. And actually we try to change this R to small r. Okay, try to change this R to small r because in this case R will be a variable. Okay, for every independent ring. Okay, so of course the R is fixed, but here we try to change the small r. Okay, from 0 to capital R. Capital R will be the radius of this disk, so that if we try to integrate R, small r from 0 to capital R, this ring become a full disk. Okay, so here we try to make these three changes according to what we get previously. So far, okay. So okay, so yeah, so okay, so actually we want to sum from. Okay, actually this sum is in quotation. Actually, it's integration of from 0 to capital R, so that this ring, as much as the radius start from 0 to capital R, okay, it becomes a whole circle. Okay, so here we introduce another charge density called the surface charge density. Okay, surface charge density, which means that the Q are uniformly distributed on the disk. Okay, so we need to consider the surface charge density. Okay, so which means that the SI unit will be coulombs per meter square rather than C over M. Yeah. So in this case, it will be like dQ equals the surface charge density times the dA. A is the area. Okay, A is the area. A is the area. Okay, so the area times the surface charge density will be the charge on the area. Okay, on the area. Okay, so sigma. Okay, so this is the small sigma. Okay, although usually you know this is the sigma. So but this is a capital letter. This is the small sigma. Okay, the small sigma, okay, remains here. Okay, so here we have dA equals to this stuff. Why it is like that? Why it is like that? Okay, so the idea here is like you try to use a scissors to cut it, and then try to expand it. Okay, hard to imagine. But the idea here is like, okay, as much as this ring is very, very thin, okay, you cut it and then expand it, it becomes something like, this is dr. And then this will be the circumference of the circle, 2 pi r. And then this become a rectangle. This become a rectangle. This become a rectangle. Okay, so okay, so this will be d small r rather than dr, d capital R. Okay, so this is a rectangle. The area of this rectangle should be the height multiplied by the width. Okay, so 2 pi r times dr. So we have 2 pi r times dr will be the area of this ring or area of this rectangle. Okay, so maybe hard to imagine for you, so but actually that's the case. If you would like to go to some rigorous mathematics, it will be something like this is this is r d theta. So dA will be like dr times r d theta. Okay, will be something like this. Yeah, because the area dA here, the area dA for this small part will be like, okay, this is dr, this is r d theta. Okay, so this is a rectangle. Okay, more like a rectangle than that one. Okay, so this is dr times r d theta. Okay, so here is only r d theta. Okay, so how to come up with the whole ring? We try to integrate the theta from 0 to 2 pi. So which means that that A will be like integrating dA will be like integrating r d theta from 0 to 2 pi. We only come up with this one, okay? So r dr will be independent to this one. So it is like r dr integration of d theta from 0 to 2 pi. So it becomes 2 pi r dr, okay, something like this. Okay, so it's a more rigorous way to explain, okay, why the area of that wing will be like this. Yeah, but this is a easier interpretation. Okay, so anyway, we would like to plug in this dq, okay, with this, replace this dq with this expression. Okay, so move it to there. Okay, so we have a sigma 2 pi r dr, and then c is placing in between. So the other stuff remains the same. And then we try to collect sigma z to here. And then these 2 pi and 4 pi, I think, okay, only pi are cancelled. Only this pi and this pi are cancelled. The 2 and 4 are not cancelled because we would like to make this one good looking. Okay, make this one good looking. Integrating 2r. Okay, yeah, because integrating r will be r squared over 2. So why not keeping this 2 here? So that integrating 2r will be r squared only. Okay, so this one will become dr squared, right? Okay, so this one will become dr squared. And actually, dr squared will be actually equals to dr squared plus c squared. Yeah, because this is just a constant. This is just a constant. So adding something here is okay. Yeah, maybe this one you are not easy to understand. Oh, so maybe I can write it like this: dr squared plus c squared over dr. Okay, so take the derivative of this stuff with respect to r. So it becomes 2r. And then z is a constant to the r, so becomes 0. So we try to move this one to the right side. So you have 2r dr equals to this one. So which is actually from here to here. Okay, so it becomes like this. Okay, so we try to put this one as negative 3 over 2 power. And then all the other constant, putting them to the front. So it is like, you can consider this is just another variable. Maybe you can call it x or whatever you like, if you are not comfortable with this big term. Okay, so it is just like integrating x to the 3 over 2 power dx, and then from 0 to r, something like this. Okay, so this is just like a polynomial. So, or polynomial, although a fractional power. Okay, but at very least, okay, so you try to add this power by 1. Okay, so negative 1/2, and then divide by negative 1/2 will be the integration, and then evaluate from 0 to r. Okay, so finally, these 2 partially cancel with this 4 to 2. And then, okay, this negative sign, okay, we try to swap the order. Okay, so nothing special. So we try to put 0. Okay, actually, r equals 0 to here. Okay, r equals 0 is like c squared, and then take the square root, and then take the inverse. Okay, so 1 over square root of z squared for this one. Okay, go to here. And then putting it r to be capital R will be like c squared plus r squared. C squared plus r squared, take the square root and then the reciprocal. So like this. Okay, so this, okay, this whole thing, okay, become here. Okay. Okay, so finally, we just distribute this c inside. Okay. distribute this Z inside, okay? So Z over C will be 1, okay? Z and C will be like a Z over square root of C squared plus R squared, like this. Okay, so this is more or less the final answer, okay, if we don't have any other assumption here. Okay, so this is the final expression, E equals sigma over 2 epsilon naught, 1 minus this stuff, okay? Also only along this z-axis, okay? So this z-axis also defined as this is the xy plane, and then z equals 0 here, and then z-axis is perpendicular to this disk. Okay, like this. Okay, so we only know the E field along this z-axis, only along this z-axis. So here, make a very strange assumption here. Okay, so here we try to assume this radius is infinity. Okay, so this is infinitely large. This is infinitely large. Infinite this. Okay, so you may ask how we can have an infinite this. Don't ask. We just make this assumption. Okay, to make the expression good looking. Okay, so actually, if R tends to infinity, okay, this term will tend to 0. This term will tend to 0. Why? Okay, so this term you can imagine it will be like Z over R, and then square root of Z over R squared plus 1. Okay, something like this. Okay, just ignore the minus sign there. Okay, and then if you just assume R, capital R is much larger than Z, because R is tends to infinity and Z is a finite value. Okay, so in that case, this one tends to 0. This one also tends to 0. So 0 over 1 is 0. Okay, so this one tends to 0. Tends to 0 if R is infinite. Tends to infinity. Okay, so this is 0. So 1 minus 0 is 1. Okay, we only get this sigma over 2 epsilon naught, which is a constant. Epsilon naught is a constant for sure. It's the permittivity. And this is sigma, is the surface charge density. Okay, which is constant. We assume the charge density is uniformly distributed over the whole disk. Okay, so this is a constant. Very great. Okay, so we can go back to the very beginning, very beginning of this chapter. Okay, so here it says, okay, if we have a plane, okay, of course this is not infinitely large, but just imagine it, because you can never draw it to be infinitely large. But in that case, it will generate a constant E field. Okay, for the right side pointing to the right, for the left side pointing to the left. Okay, it is just this case. Yeah, going back here. So this is great. So so actually we will derive this expression again in the next chapter using the Gauss law. Okay, but yeah, here we use the integration to come up with that. Okay, using all these steps. Actually, also applying the step in the Pufis case with the charge ring. So you can feel that, okay, well, using the calculus is very tedious. Okay, it just takes more than an hour to really derive this formula out. Okay, anyway, so let's go to another topic first. So here, it is to mention a point charge in an electric field. Okay, so actually, at the very beginning, it is just like the definition. E is defined as F over the Q. Okay, F over the Q. So this is just like moving Q to the other side. So it means that if you just put a charge in the E field, then there will be a force acting on the charge. Okay, so this is the highlight, the electrostatic force or the Coulomb's force acting on a charged particle located in an external E field has the direction E if the charge Q of the particle is positive, and has the opposite direction of if Q is negative. Oh, very straightforward. Yeah, and here is the mechanism of the inkjet printer, 就是喷墨打印机啊，喷墨打印机. Okay, so actually it is like, for example, this is the green color. This is the green color. We try to split a small ink out, and then we try to add some charge. Of course, controlled by the computer. Okay, we try to add some charge to a dot of ink. Okay, so we add some charge there. So as much as the ink have a similar mass, and then we try to change the amount of charge adding on the ink, then it is like, okay, so here we try to apply parallel plate. Okay, here with plus, okay, all the way plus, and then here we have negative plate, negative charge. Okay, so we have the parallel plate here. So inside this region, we will assume that there will be a uniform, roughly a uniform E field pointing downward, according to what we get here. Okay, so this if it is a positive charge, okay, all the E field will be like pointing upward for the top part, or pointing downward for the bottom part. If this Q is positive, if the Q is negative, all the E field pointing downward. And then the E field pointing upward for the bottom part. Okay, something like this. Okay, so here we try to make it like, okay, the positive charge on the top plate and the negative charge on the bottom plate. So both generate E field pointing downward. Okay, so we will assume that the E field are all uniform between the two parallel plates. Even though it is not infinitely large, but at very least, near the central part, okay, will be more uniform. Okay, near the edge will be not so uniform, but at least it will be like that. Okay, so here try to accept that there will be a constant E field pointing to the bottom. So in that case, we try to add some charge, or Q is negative to an ink. Okay, so maybe I use the green color. Okay, try to add some charge Q less than 0 on the ink. So inside the E field, okay, as much as this is a negative charge, there will be a force, okay, a force pointing upward. Okay, 就是有点类似那个炮射运动，高中学的那个炮射运动。But okay, but this is upside down. Okay, so we try to change the amount of Q so that we can control the displacement, X or whatever direction. Okay, so try to change this direction so that we can control where the ink goes. Okay, so this is a sample problem. So here it says the deflecting plate on an inkjet printer with superimposed coordinate axis, an ink drop with mass, okay, with mass M, okay, mass M, okay, of this, and then a negative charge of magnitude Q, okay, Q, enters the region between the plate, initially moving along the x-axis with speed Vx, okay, speed Vx， OK， 就炮式运动嘛，然后也没有阻力了，所以它 Vx 就不会变。OK, so the Vx won't change along this whole path, and the length of the L. The length L of each plate is 1.6 centimeter. Okay, so this is 1.6 centimeter. And the plates are charged and thus produce an E field at all points between them. Assume the field is downward directed. Okay, so the E field is downward directed. Okay, so which means that the force is pointing upwards. Uniform and has a magnitude of so this is the okay, so this is the E field. What is the vertical deflection of the drop at the far edge of the plate? The gravitational force can be neglected. Okay, so first of all, we would like to have T. T will be 0.016. Okay, because centimeter is not SI unit, meter is SI unit, so we need to convert centimeter. 1 centimeter is 0.01 meter. Okay, so 1.6 centimeter is 0.016 meter. Divided by Vx, which is 18. So it takes 8.89 times 10 to negative 4 seconds to go through. Okay, so this whole path takes t to go through. So next, F equals QE. So Q, okay, actually capital Q here will be 1.5 times 10 to negative 10 to negative 13, and then times 1.4 times 10 to the fourth power, okay, which is this one. So this is 2.1 times 10 to negative 7 Newton. Okay, so this is the force. This is the force acting on the drop. Okay, so according to what you have learned in the mechanics, okay, so you have y equals 1/2 at squared. And then according to Newton's second law of motion, a is f over 2m and then t squared. So it will be 2.1 times 10 to negative 7 over 2 times m. M is 1.3 times 10 to negative 10 times this t is 8.89 times 10 to negative 4 square. So finally, it is 6.4 times 10 to negative 4 meter. Or you can express it as 640 micrometer. Okay. Yeah, in the quiz you can answer either of them is enough. You don't need to answer both. Yeah, but the one point is that you need to memorize the scientific prefix. The scientific prefix. Okay, you need to memorize. Don't ask me during the exam. I will not tell you. So there are some you need to memorize. So let's say giga is 10 to the 9th power, mega is 10 to the 6th power, kilo is 10 to the 3rd power. So all of this, if you are familiar with the computer, you should be able to, you should have memorized it. And yeah, if you go to the negative part, it will be like milli. Okay, milli is 10 to negative 3rd. Micro is 10 to negative 6. Nano is 10 to negative 9. Pico is 10 to negative 12. Femto is 10 to negative 15. Okay, so you need to memorize all of this. Yeah. Yeah. Don't ask this during the exam. I'll not answer. Yeah, because even though you don't try to express it in the answer, but yeah, sometimes the question sometimes have this kind of scientific prefix. So you need to know, and you need to know. Because it's not too many, okay? Actually, if you're familiar with computer, you always seeing this, okay? Even though for the 10 to the 12 will be tera, okay? T, okay? Yeah, for your hard disk, okay? You probably have a terabyte hard disk. Okay, milli should be known, even for primary student. Okay, micro, nano, femto. Okay, so just 4 of them you need to remember. Okay, so the final part in this chapter is like if we try to put a dipole. Okay, so just now we mentioned if we put a charge inside the E field, what will happen? Okay, so this part is a little bit more complicated, although I don't think we will have too many questions about that. Okay, but anyway, it is some sort of physics. Okay, so the case is like if we put a dipole in a uniform E field, what will happen? Okay, so it is like this. Okay, so we assume there is a E field, a uniform E field pointing to the right side, okay? So all of these are the E field. All of the blue arrow are the E field. Okay, here, let's assume we put the dipole with an initial condition like this, and then it is not changed at all. It is not changed at all. It is totally stationary at this position. Okay, so here we try to see, okay, what will be the force acting on the charges. So this one is a positive charge, and then the E field point to the right side. So there will be a force pointing to the right side acting on the positive charge. And for this negative charge, E field pointing to the right side, so the force will be pointing to the left side. Okay, so this is the force acting on the negative charge. Okay, so it will be like this, okay? So it will be like this, okay? It will be like this, okay? Swinging back and forth, okay? If you don't believe, you try to take something out and then you try to do it yourself, and then you will know. Okay, so it is just like swinging back and forth, and actually, in the physics, the physician call it the torque, 力矩. Okay, the torque on the electric dipole of the dipole moment P, when placed in an external E field, is given by a cross product torque. The tau, okay, this is tau is P cross E. Okay, the cross product. Okay, yeah, I guess you should have learn it in high school physics when you learn the electromagnetism. But we will cover the cross product later on when we talk about the magnetism. Yeah, but anyway. Okay, so as much as this is the dipole moment. Okay, so this is the dipole. Okay, negative QQ here. So the D is pointing to the top right. Okay, so as the P, the dipole moment. The electric dipole moment is also pointing to the top right. Okay, so P is like this, and then E is pointing to the right side. So the cross product will be like you pick out your hand and then point to this direction, cross to the right side, and then your thumb point into the page, go into the page. So which means that the torque, the tau, is across the torque here. Okay, the torque here is actually pointing into the page. So which means that it is like, for this moment, it is like rotating clockwise. Okay, but after swinging to this position, it will be swinging back. Okay, like that. Okay, so that is the case. And then, yeah, it will be like the magnitude of this vector multiplied by the sine of the angle between them, okay? And then the potential energy will be negative P dot E, okay? So, which means that if you have the expression of P and the expression of E, then you will get the torque and the potential energy, So we will not cover that too much because it is more like a mechanical knowledge. Okay, so I suppose most of you are civil engineering students, so you'll be you should have known it better than me. Yeah. Okay, so okay, so maybe we stop here today.